Alright, thanks for watching, and today I want to solve one of the most basic PDEs, but also that are one of the most important ones. Because it turns out the PDE I'll write down now, you can use it to solve the wave equation, which I'll do in another video. So today's goal is to solve what's called the transport equation, and at this point, it's not clear why it's called the transport equation, but you'll see later that when you see the solution, you'll be like, of course it's a transport equation. And it's given as follows. So our goal is to solve the following PDE. So ut plus b dot du equals to 0, and u of x0 equals to g of x. Let me explain this gibberish in case you don't know PDE notation. So first of all, u is a function of two things. It's a function of x and t, where x is in Rn, and t is time is in 0 infinity. So that's first of all, we have a function of x and t, where x, if you want, is a vector, x in Rn, and t is in time. B, it's a constant vector, so think b as being b1 up to bn. And du, that's just the gradient of u and x. So du, that's just another way of writing ux1 dot 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 uxn. Some people, they write it as gradient of u like that, but it turns out that's very bad notation, because let me tell you why. Consider this. Gradient squared of u. What is that? Is that the Hessian, like the matrix of second derivatives, or is that the Laplacian? That's why, in my opinion, it's bad to write this. It's better to write du and to write Laplacian as a triangle u. Okay, great. So what this tells you is that the time derivative of u plus b dotted with du equals to 0, which means b1 ux1 plus dot 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 plus bn uxn equals to 0. So ut plus this equals to 0. So for example, think of a concrete example. It would be in 3 dimensions, for example, it would be ut plus 3 ux plus 4 uy minus 2 uz equals to 0, where in this case b is 3, 4 minus 2. So we'll be able to solve a very general class of PDEs, first order constant coefficient ones. And here's how to solve it. Basically, what we want to do, we want to take this equation and somehow transform it into u prime equals to 0 in a more sophisticated way. And if u prime equals to 0, you in fact get u equals to a constant. The question is, how can you achieve this? Well, here's the cool thing. We're going to think of x comma t as its own variable on its own. So let y be x comma t, which again you can think of x1, x2, dot 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 xn comma t. Then rewrite this equation. Which I just erased, but let me rewrite this. So ut plus b dotted with du equals to 0. Notice you can write this as b1 ux1 plus dot 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 plus bn uxn plus 1 times ut equals to 0. But this is the same thing as saying b1 dot 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 bn1 dotted with ux1 dot 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 uxn ut equals to 0. So in particular, if you want to define this vector A, let's say, to be the vector b comma 1, then this says A dotted with the derivative of u with respect to this new variable, so dy of u equals to 0. And that's very interesting because it explains the thing I explained, it illustrates the thing I explained before. I told you that you want to take this equation and write this in terms of, derivative of u equals to 0. Well, in fact, you've done that. What you've shown is that the directional derivative of u in this direction is actually equal to 0. And you might say, hey, directional derivatives, this means that, the vector has to have length 1. Well, no problem. Just divide it by the length of A, and you still get that. Indeed, the directional derivative of u in the direction of the vector b1 equals to 0. And if the derivative of u equals to 0, it means that u is constant. So, really, u is constant on the line of directed by b comma 1. Or in other words, on the line with slope b comma 1. And let's just find a parametric equation of that line. So suppose you start at xt and you go in the direction b comma 1, then a parametric equation would be given by simply x plus sp and t plus s, where s is in R. Right? Because you start at x, you go in the direction b, in the x direction, and then you go in the direction 1 in the t direction. And I forgot to say, all this right now is gibberish. Let me now do the actual proof, but the proof needed this as a motivation. So now let me be a little bit more concrete. Namely, consider now the following thing. So consider well, as I said, u is constant on that line. So in particular, let's consider the values of u on that line. So in particular, z of s is equal to u of x plus sp t plus s. So again, the line is given by this, and we want to calculate the values of u on that line. Well, ideally, since u is constant on that line, the derivative of z equals to 0, well, let's show that now. So, z prime of s, let's see. Now, as is usual in PDEs, we want to use a chain loop. So, let's do it step by step. So, it's ux1 of this thing. So, x plus sp, t plus s, and you want to differentiate this with respect to s, so times x1, times b1, but you differentiate it with respect to s, plus dot dot dot, you do everything in the n components, x plus sp, t plus s, bn, and lastly with the t component, that's ut, x plus sp, t plus s, times 1. Okay, that's all in good. And now, let's just rewrite this in terms of our equation. This is really the same as saying b dot du of x plus sp, t plus s, plus ut, x plus sp, t plus s. And in particular, let's forget now the things inside. So it's b dot du plus ut. And so in particular, since our equation holds at every point, it holds also at this point. So in fact, this equals to 0. So we have shown rigorously now that the value of u along those lines equal to 0. And we're almost done. You might say, how is that useful? Well, so now we have two things. Consider u of xt, what we want to find. And on the other hand, we have z of s, that's u of x plus sb t plus s. And the question is, how are those two related? Notice that if you set s equals to 0, then you do get u of xt. So u of xt, that is z of 0, right? Because it's u of x plus 0s, 0b, t plus 0. And here comes the important thing. First of all, why do we use this? Because ideally we want to relate u with the value at 0. And remember that u of x0 was g of x. Well, in particular, notice that we can get u with the value at 0 at minus t. And here is where we use the fact that z is constant. Because u is z of 0 and z is constant, this is the same thing as z of minus t. And now, just like magic, the formula will pop out. So it's u of x minus tb and t minus t. And that's u of x minus tb 0. And because u at 0 was g, that is g of x minus tb. And therefore, we get our formula, u of xt is g of x minus tb. How cool! This is the explicit formula for the transport equation. And you may ask, why is that called the transport equation? Because literally, if you have any initial value here, let's say g of x, this gets transported along the line, directed by x comma 1. So, directed by b comma 1. So it's really cool. And in fact, using the same idea, we can actually solve a more complicated transport equation. In fact, let me do this. We will need this for the wave equation. In fact, what about in the transport equation, what if we don't have 0 anymore? So now let's consider the inhomogeneous version. So ut plus b dot du is f of xt, and u of is x comma 0 is g of x. Well, again, if we use this trick of letting y to be x comma t and a to be b comma 1, then you can transform this into a dotted with the y derivative of u equals to f, which sort of tells you that u prime equals to f, so u should be the integral of f. But again, this is non-rigorous gibberish. Let's make this rigorous with our function z. So just like before, let z of s to be the value of u on that line. So u plus sb and t plus s. Shout out to UCSB, okay? All right, and now let's see what z prime is. again, just as before, if you want to do this in components, you can, but using the Chen-Lu, this equals the derivative of u with respect to x, dotted with this thing, so derivative with respect to s is just b, and plus ut times the derivative of this with respect to s, which is 1, so du dotted b with ut, and by our equation, this equals to f, so if you want f of x plus sb t plus s. And so what do we get? We get z prime of s equals to this whole thing. So in particular, so z prime of s equals to f of x plus sp t plus s. So in particular, z is the integral of f. But now let's be a little bit clever about this and choose very good endpoints. Because of course, we had the z of s to be u of x plus sp t plus s. Of course, we want to relate the value of z at 0, because this gives us u of xt. But also, we want to use this g function, and the way to get the function g is to set this equal to 0, but if this equals to 0, that means that s is minus t. That's why we want to integrate from minus t to 0. So z prime of s ds equals to the integral from minus t to 0 of f of x plus sp t plus s ds. And that's very good, because this becomes z of 0 minus z of minus t. Z of 0, that is u of x plus 0b t plus 0, which is u of xt. And minus, if you set s equals to minus t, that becomes u of x minus tb, t minus t, which becomes u of x minus tb 0, which is g of x minus tb, just as before. And therefore, what do we get? The left-hand side then becomes u of xt minus g of x minus tb equals to the integral from minus t to 0 f of x plus sp t plus s ds. You can leave it as that, but it's a little bit ugly. It might be better to use a little change of variables just to, get it back from 0 to t. And well, the change of variables, if you want, is that s prime, if you want, s prime is good, is t plus s. Then, ds prime is ds. And moreover, at s equals to minus t, s prime is 0, and at s equals to 0, s prime is t. So this becomes integral from 0 to t of f of x plus, so s becomes s prime minus t b, and then s prime ds prime. And well, now we can just remove the primes if you want, or just let s prime equals to s or something, and that's fine. And so we get, again, u of x comma t minus g of x minus tb is integral from 0 to t f of x plus s minus t b s ds. And as I said, the magic of this is that our solution, whatever it is, pops up. So then u of xt is g of x minus tb plus integral from 0 to t f of x plus s minus tb s ds. So that's really neat. Even this more complicated inhomogeneous equation we were able to solve. And the interpretation of this is u is, g, but transported along that line, plus some sort of a running cost from 0 to t. So think of a payoff or something. And by the way, so here's the cool thing. This function z is very important. In fact, it turns out almost any first order PDE you can solve in this way. Except what happened here was that z was along a line. In general, the line just becomes curved, and we get that u is constant along a curve. And of course, and to find the curve, you have to solve what is called a characteristic equation, which is really neat, because what if you have the following scenario? What if you have two curves that intersect? Then on the one hand, u is one value here, but another value here. And if the two values are different, here we get a problem. And the question is, what do you do? How do you define, the solution after such a shock? And it has to do with entropy, called an entropy condition. But this is like for way later if you want. Alright, so I hope you like this little PDE extravaganza. If you want to see more PDEs or more math, please make sure to subscribe to my channel. Thank you very much.